Hey guys, today I will be discussing the binomial theorem, what it is, why it's useful, and how you can use it, along with some patterns that you can see in an expanded polynomial that has gone through the binomial theorem. So let's get started. What is the binomial theorem? The binomial theorem is a result of expanding the powers of binomials, or the sums of two terms. So, in other words, it's a quicker way of expanding or multiplying out a binomial expression raised to an inconveniently large power that would be much harder to multiply out by hand. For example, if we look at a binomial as a term simplified to parentheses a plus b to the power n, where a plus b is any binomial and n is a whole number, this is an example of a binomial that would be hard to solve by hand. Parentheses 3x plus 5 to the power 45 is a really big binomial, as opposed to 3x plus 5 to the power 1 or 2 or 3, which could be simplified by hand. But it would just take hours trying to simplify this one. So, let's move on. Why is the binomial theorem useful? As I just noted in the previous slide, it's a much more efficient way of expanding binomials that are raised to higher powers. But also, it is used in many math problems across several different subjects in math, like combinatorics, which is a branch of math that deals with combinations of objects belonging to a finite set, algebra, calculus, and many other areas of mathematics. Next, the binomial theorem. So, there are two main forms of the binomial theorem equation that we can use, but of course they mean the same thing. So in this big red box we have the expanded form, and then the smaller one we have the condensed form. Let's take a closer look at the expanded form. So the equation we have here simply states that parentheses 1 plus x, or any binomial, to the power n equals n choose 0 plus n choose 1 times x plus n choose 2 times x squared plus so on and so forth, which simplifies into n sigma k equals 0 times n choose k times x to the power k. The n ck, which is n choose k, simplifies into a factorial form that states n factorial over k factorial times n minus k factorial, where n is a positive integer. So, this may seem like a lot of variables, but let's go and go through every single variable one by one. So the n is, as stated here, a positive integer, and it's the exponent which is of the binomial. So this could be, for example, 40. This exponent will determine the k value and how far you have to go. So k determines the term number, and if the n value is, say, 40, that means that there will be 40 sets of these, because you increase from 0 to 1 to 2 all the way up to 40. Next, let's look at the condensed form. The condensed form in other variables, a plus b means the same thing as x and y, to the power n equals n sigma k equals 0 times n choose k times x to the power n minus k times y to the power k, where k again is equivalent to the term number, and x and y are the binomial, and n choose k has a factorial value that simplifies into n factorial over k factorial times n minus k factorial. Now, this may seem like it's a little complicated at first, but let's break it down with an example. But first, let me simplify a factorial to review what a factorial really is. So all that a factorial is, for example, 5 factorial, is the number 5 multiplied by every number that is 1 less than 5. In simple terms, it would mean that 5 times 4 times 3 times 2 times 1 is equivalent to 5 factorial, or 5 factorial equals 120. That's 5 times 4, 20, times 3, 60, times 2, 120, times 1, 120. So that's just a review on factorials to understand how to set up this part of the equation, which is equal to n choose k. Now let's go on to an example using the binomial theorem so we can break the equation down. So over here I just put the equation for n choose k in the factorial form in the top corner to reference back at, and an example of a binomial that we'll be going through. So suppose that we have a binomial raised to the power of 4. This would be the equation that we would set up for it. N value would be 4, k would always equal 0, and n over k, which is n choose k, times a to the power of 4 minus k times b to the power of k. Now, to simplify that, what we do is repeat this segment of the equation 4 times, starting at 0 as the k value. So all we did was put the k value here starting at 0. So if k equals 0, then a to the power of 4 minus k is simply a to the power of 4 minus 0, which is a to the power of 4. And b to the power of k is just b to the power of 0, or 1. So there's no b here because it's just equivalent to 1, and 1 times a to the power of 4 is a to the power of 4. So you go on doing the same thing, taking into account of a to the power of 4 minus k and b to the power of k, until you have reached the k value that matches your n value. Now after doing that, this is your final expanded form. Now it's time to make sense out of these. So all I did was order up these fragments and simplify them in factorial form. So all that 4 choose O means is 4 factorial over 0 factorial times 4 factorial, according to this equation, which says k factorial times n minus k factorial is what n choose k is equivalent to. So, since we know what the factorials mean, let's look at this example. 4 factorial is simply 4 times 3 times 2 times 1, and 1 factorial times 3 factorial is simply 3 times 2 times 1. To simplify factorial, all you must do is cross out the similar digits in both the numerator and denominator. And so in this case, 3, 2, 1 is common in both. So if you cross that out, all you're left with is 4 in the numerator. And so that is what this factorial is equal to. So after completing all of them, you will get the pattern that I was talking about, 1, 4, 6, 4, 1, or I haven't talked about it yet. But this is similar to the pattern in a distribution, as it goes increasing and then it decreases the same amount. And then you can use these numbers as the coefficient for your final expanded form equation. So taking a to the power of 4 plus, it's simply replacing the factorial part with numbers. So replacing the 4 choose area with numbers. So you replace 4 over O with 1, and replace 4 over 1 with 4, 4 over 2 with 6, 4 over 3 with 4, and 4 over 4 with 1 to get a to the power of 4 plus 4 times a to the power of 3 times b plus 6 times a to the power of 2 times b to the power of 2 plus 4 times a times b to the power of 3 plus b to the power of 4. So Hopefully this doesn't seem as intimidating as it might have seemed at the beginning. Now, patterns. Like I stated earlier, one similar pattern in all expanded forms of binomials, this is just the same one that I used in the previous example, is symmetry. You can see those through the coefficients of the final expanded equation, 1, 4, 6, 4b. It forms a distribution, and so there is symmetry if you put a line through the middle term. Another pattern that you can see in the polynomial that results from expanding this binomial is that the exponent of variable a descends as you go from left to right. What I mean by this is that the exponent decreases by 1. So a to the power 4 goes to a to the power 3, to 2, to 1, to 0. And the same pattern is seen, but in the opposite direction with b. So instead of increasing, instead of decreasing, it increases from left to right. So from 0, it goes to 1, to 2, to 3, to 4. So these were just a few quick patterns in the binomial theorem, and I hope that this made it a little easier for you to understand. Thank you for watching and listening.
Alright guys, so I hope you're following along and you still don't know what the binomial theorem is, but if you're like me and your head hurts a lot and you're super lost, we're going to take a quick break. History break with a globe. We're going to travel from 21st century USA all the way to small little country of France. If you're wondering why I said 21st century, we're actually going to be traveling back in time to 1623 France. If you're wondering why we're traveling to 1623 France, we're going to meet this guy. This guy is named Blaise Pascal, and he was the creator of Pascal's Triangle. He was born in Clermont-Ferrand, France, probably mispronouncing that, in 1623, where we are now. Now, most assume that Pascal invented the triangle because it is, of course, named after him, but in fact, he was one of the great users of the triangle, but did not invent it. If we want to learn who invented it, we have to travel back to the 11th century and all the way over to the large country of China, where we can meet this guy. From the 11th century of China, Jia Shen, a Chinese mathematician, historians say was the first one to invent Pascal's triangle, but unfortunately was named after Pascal. Now we're going to travel back to 21st century United States, where we'll be in West Orange, learning more about why we are learning about Pascal's triangle. This, everyone, is Pascal's triangle, but to understand Pascal's triangle, I feel like we should make one ourselves and understand why it looks like this. So, let's make Pascal's triangle. Pascal's triangle is set up similar to a maze. If we start with a 1 at the top, how many different ways can we go from 1 to another number? One way. So we'll fill in another 1. One way to get here, there's a 1. Now, if we split it up into 2 again, how many different ways can you get to this spot in the maze? One way. But how many ways can you get to this spot in the maze? You can go this way, or you can go this way. 2 ways. How many ways can you get here? One way. The horizontal rows also, interestingly enough, when read from left to right, equal 11 to that row's power. So for the 0th row, 11 to the 0th power equals 1. There we go, 1. 11 to the first power is 11, 11. 11 to the second power is 121, 121. 11 to the third power is 1,331, 1,331. If we skip down to something like the 11 to the 6th power, although it's right across, you do need to do a little bit of addition, so we'll do that for you. First of all, 11 to the 6th power is 1,771,561. 1,000,000, 6 plus 1 is 7, and 5 plus 2 is 7. Keep the 1, keep the 5, keep the 6, and keep the 1. You get 1,771,561. Now, if you got lost at any point during that pattern, it was one of the more complicated ones. Now we're going to look at one of the more simpler ones. This pattern is saying that two numbers atop from one number, when added together, make that number. 1 plus 2, 3. 1 plus 4, 5. If we jump around over here, 10 plus 5, 15. 21 plus 35, 56. If you do the calculations on your calculator, 84 plus 126 does equal 210. This works for any spot on the triangle, even if you continue to more rows or anything, it works no matter what. Another pattern on Pascal's triangle is called the hockey stick pattern. This basically says that if you make a hockey stick in the triangle, something that looks like that, a little hockey stick, you can add up all the numbers in the stick and they equal the bent part. 1 plus 3 plus 6 plus 10 plus 15 does in fact equal 35. If we take a look at another example, make this hockey stick over here. 1 plus 7 plus 28 plus 84 equals 120. The only rule is that you must start with a 1 on the end of a row and make a hockey stick. That's it. So have a little fun, make some hockey sticks if you're into hockey, and check out this pattern. This now is Sierpinski's triangle, and we're going to use it to show you the next pattern that has to do with Pascal's triangle. Now you ask, what is so similar about Pascal's triangle and Sierpinski's triangle, besides the fact that they are triangles? I'm going to show you. In Pascal's triangle, if all of the cells that were odd numbers were shaded black, and all of the positions containing even numbers were shaded white, eventually you will get to Sierpinski's triangle. Now, what do I mean by that? I'll show you. Luckily, all of our cells are shaded white. I'm going to go ahead and shade the odd number cells. Alright, so with my ugly pen-shaded triangle, you may not exactly see this, but when you take a larger Pascal's triangle and go for an extremely long time with shading, eventually it looks like this. If you zoom in, this was the triangle that we used approximately, and as you shade more and more and more and more, you get Sierpinski's triangle. Exactly alike. This is personally my favorite pattern, as I didn't realize how they would look alike after all the drawing and fun, and less math and calculations. You can finally see the similarities.
The binomial theorem tells us that m plus n raised to the 5th power is equal to the sum from k equals 0 to 5 of 5 choose k times m to the 5 minus k power and n to the power of k. Starting with k equals 0, m plus n raised to the 5th power equals 5 choose 0 times m raised to the 5 minus k power, which is 5, and n to the power of 0, which is 1, plus 5 choose 1 times m raised to the 5 minus 1 power, which is 4, and n to the 1st power, plus 5 choose 2 times m to the 3rd power and n to the 2nd power, plus 5 choose 3 times m to the 2nd power and n to the 3rd power, plus 5 choose 4 times m to the 1st power and n to the 4th power, plus 5 choose 5 times m to the 0th power and n to the 5th power. Now that we've expanded the equation, we need to figure out the coefficients for each term. To do this, we have to apply n factorial over k factorial times n minus k factorial over and over again. So 5 choose 0 is equal to 5 factorial over 0 factorial times 5 minus 0 factorial, which is 5 factorial. For this, we will define 0 factorial as 1, so this is just 5 factorial,
which is 1. So the coefficient of the first term is 1. 5 choose 1 is equal to 5 factorial over 1 factorial times 5 minus 1 factorial, which is 4. This equals 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1, which becomes 5 because 4 times 3 times 2 times 1 cancels out. Five choose 2 is 5 factorial over 2 times 3 factorial, which is equal to 10. Five choose 3 is 5 factorial over 3 factorial times 2 factorial, which is also 10. Five choose 4 is 5 factorial over 4 factorial times 1 factorial, which is 5. And 5 choose 5 is 5 factorial over 5 factorial times 0 factorial, which is again 1. So m plus n raised to the 5th power equals m to the 5th plus 5m to the 4th times n plus 10m raised to the 3rd power times n to the 2nd power plus 10m to the 2nd power and n to the 3rd power plus 5m times n to the 4th power plus n to the 5th power. Just like the other problem, this equation is equal to the sum from k equals 0 to 4. 4 choose k times 2x to the 4 minus k power and 1 to the power of k. Starting with k equals 0, 2x plus 1 raised to the 4th power equals 4 choose 0 times 2x to the 4th power and 1 because 1 to the power of 0 is 1. 4 plus 4 choose 1 times 2x to the 3rd power and 1 to the 1st power. Plus 4 choose 1 times 2x to the 2nd power and 1 to the 2nd power, plus 4 choose 2 times 2x to the 2nd power and 1 to the 3rd power, plus 4 choose 3 times 2x to the 1st power and 1 to the 3rd power, plus 4 choose 4 times 2x to the 0th power and 1 to the 4th power. Now that the binomial is expanded, we have to find the coefficients. So 4 choose 0 is 4 factorial over 0 factorial times 4 factorial, which is 1. 4 choose 1 is 4 factorial over 1 factorial times 3 factorial, which is 4. Four choose 2 is 4 factorial over 2 factorial times 2 factorial, which is 6. Four choose 3 is 4 factorial over 3 factorial times 1 factorial, which is 4. And 4 choose 4 is 4 factorial over 4 factorial times 0, which is again 1. And to determine the final product, we need to find what 2x raised to the 4 minus k power is and multiply it by the coefficient we just found. So 4 choose 0 is 16 because 2 to the 4th power times 1 is 16. 4 choose 1 is 32. 4 choose 2 is 24. 4 choose 3 is 8. And 4 choose 1 is 4. So 2x plus 1 raised to the 4th power is 16x to the 4th plus 32x cubed plus 24x squared plus 8x plus 1. To find the 5th term of 4x minus 3 raised to the 8th power, we need to first write out the 8th line of Pascal's triangle. This will determine the coefficients in each term in the final product. They are 1, 8, 28, 56, 70, 56, 28, 8, and 1. And the 5th term is 70. So this term will be 70 times 4x to the 9th power times negative 3 to the nth power. And remember to put 4x and negative 3 in parentheses. So to find the exponent for 4x, we need to count backwards from 8 to 0. And the 5th term is 4. And to find the exponent for negative 3, we need to count forward from 0 to 8. And again, the 5th term is 4. So while we have this, we need to multiply each number by the exponent. So it would be 70 times 256 x to the 4th times 81. And the final result will be 1,451,520 x to the 4th.
All right, this concludes our lesson on Binomial Theorem and Pascal's Triangle. We hope that whoever's watching this video has learned something from it, and thank you for watching.